So hello, I'm José Ricardo Correia. I'm a postdoctoral researcher at the University of Helsinki and the Helsinki Institute of Physics. And in collaboration with Carlos Martins, so my former PhD advisor and a researcher in the University of Porto, the Center of Astrophysics for the University of Porto, we have an ongoing project in LUMI. So the name of the project is, the name is GRACOS, which is sort of one of these fake acronyms that people kind of force in astronomy. It comes from gravitational and cosmic strings. Basically, just to explain what these two things are, I think the best part is to start from sort of a simple analogy. So the same way that, for example, one takes a container with water, and as the container cools down, eventually this water transitions to ice. This doesn't happen completely homogeneously, right? So one will have sort of small patches of ice forming, etc., and you will have sort of cracks in between. Now, in the early universe, it's quite plausible that something similar might have happened. And if these cracks are filament-like, or sort of like long, very long wires, then they are known as cosmic strings. So these are the objects that we try to study. At the LUMI project, we're basically trying to use very high-resolution simulations to accrue enough statistical data to improve our understanding of the evolution of these objects. Not just, say, a single one of them, but, for example, an entire network or mesh of them. This is important, or at least it's connected to the observational consequences that we expect from them. For example, we want to know what gravitational waves are emitted by these objects and by the whole network throughout cosmic history. The main motivation to look for these sort of objects is that although, say, our standard models of particle physics and even of cosmology have some predictions, they must be necessarily incomplete, because there are things which cannot be explained with the current ingredients. So, of course, if I have to try and propose some sort of theory of new physics, I'm going to add some extra ingredients. As these extra ingredients are added, some subclasses of these theories predict the formation of these strings. Right? So in some sense, we are looking for these strings specifically as a sort of a smoking gun, or as a way to at least see some evidence of these sort of models of physics beyond the standard model, right? So, of course, if we don't find anything, it also tells us another important piece of information, which is what these models are not necessarily, right? So it tells you, okay, they cannot form strings at these energy scales, for example. Right? So it's also an important question in the other way. So the flip side is also. The experience using LUMI, I would probably divide it in two parts. So one initial part, which was very exciting, because essentially the type of graphics processing units that LUMI uses by AMD, so the MI250X, were not graphics cards that I had used before, right? So I was just used to using NVIDIA products. And having changed to a different machine, to a different architecture, okay, on one hand, it's still graphics processing units, so they still function in a rather similar way, but there's always an adaptation process, right? So there's always a matter of trying to port one's code, of trying to use new libraries and new tools. So I think that was the first initial part, which was very exciting and very fun. The second part, also exciting and fun, but less from an HPC point of view, which was mostly the part about trying to use LUMI's horsepower to try and, as I mentioned, accrue large amounts of statistical data to try and study specific events in high-resolution networks, right? So previously this was very difficult to do. It still is somewhat difficult in a sense, but LUMI's computational horsepower, let's just say that it's one of the few machines in the world that allows us to still do this, to actually do this right now. So basically, apart from this machine, I'm pretty sure that within Europe, one would have to go with either less statistics and or less resolution. So it is a crucial part of the project that we use LUMI for our kind of results. Oh, the experience was quite pleasant. So, of course, as I mentioned, using a new machine, there's going to be a few hurdles, and there's always going to be certain, I would say, almost idiosyncrasies of the machine, almost, that one needs to learn about or know. And, of course, eventually, it's natural to need help. I think the user support team has always been very quick and very helpful in answering to any of the questions I've had. I think they never take more than a single day to reply, which is fantastic. Oh, I always need more. But so, well, again, it's a bit difficult to know 100% at which point will we have, say, the good proper model or the correct resolution necessary to at least extrapolate this to the entire cosmic history of the universe, so the whole evolution of the network. So it's not something one can calculate or even simply just write down or hand wave even and just write down in an envelope. The only thing I know is that so far it seems that the higher the resolution we're implementing, the less it seems to change. So we might be getting closer and closer to the correct answer. So it's positive in that sense.